Go ahead and take a minute and read the problem statement. So in what truly can only be described as a freak accident for sure. On the plane, however, are two strain gauges. We know the values on those strain gauges. This is clearly a case of plane stress. So we're going to take those strain gauge readings, turn them into some stresses, and find some principal values as well. So as soon as you see plane stress, you're going to want to highlight to yourself, just remember that sigma zz is equal to 0. Epsilon zz can be calculated. We don't end up calculating it in this problem, but it's a good thing to remember. So let's go down and take a look at our plane stress value. So there's our 3D Hooke's law. We use epsilon xx, epsilon yy equations. Right, we've got zeros for sigma z. So we can go ahead and put that in the form of ax equals b. Maybe use a calculator. And so you would just solve that equation by x is equal to a inverse times b. In doing that, you would find your initial normal stresses, xx and yy, to be of those values. However, we do not know what the initial strain is. We certainly don't know that it's 0. We wouldn't want to say that. What we're going to do is just put it on the strain state. It's just unknown. So then here again is our initial stress state in the x direction. In the y direction, we've got normal stresses. We've got an unknown shear stress. And we're going to be able to calculate it based on some things that were said in the problem statement. So we'll get this thing going on to Mohr's circle. So the way we've drawn it, right over on the x face, we've got positive 10.57. And we'd have negative tau. We don't know what that is. It's negative because on Mohr's circle, clockwise is positive. So we've got a shear stress that would cause the element to rotate in the counterclockwise direction. So on the y-face, we've got 12.49, comma, plus tau. So we'll put this on Mohr's circle. Let's go ahead and plot those 2 points. There's the x point. There's the y point. And remembering that clockwise is always positive for shear stress. Calculate the center of that circle, which is just sigma average. So we're going to add the two normal stresses, divide by 2, giving us 11.53. We can find the radius of that circle, at least by equation, not by total value, but we'll be able to find it by r squared, which is equal to the length of that side squared plus the length of that side squared. So we do have a value of 0.96, and so r squared is equal to tau squared plus 0.96 squared. So to kind of unlock this problem, what we need is the shear stress. So go back and look at the problem statement. It says, knowing that on any angle, the minimum normal stress is exactly 0, i.e. a principal stress is equal to 0. So we can see from our formulation, one of the principal stress is going to be up here, right, for the in-plane direction. The other one is going to be right there. Right, by the problem statement, it says that one of them is equal to 0. So let's just go ahead and apply that sigma 2 is equal to 0. Right, that would mean that twice the radius, or the diameter, is still going to be sigma 1 minus sigma 2, but sigma 2 is equal to 0, so it's just equal to sigma 1. So we've got an expression for the radius. Got 2r is equal to sigma average plus r. So all we've done is taken the 2, thrown it back over there, and the expression for r is equal to sigma average. So the radius of the circle is going to be 11.53. So we're just going to take that information and go ahead and plug it right back into equation 1. And we can go ahead and do our math, and it tells us that tau is equal to plus or minus 11.49 KSI. So now with the known value of tau, we can go ahead and calculate the pink theta. So I'm just going to scroll right back up here. If we look at that angle, right there is the one that we're talking about. That would be the pink theta. And so we can now calculate it as 85.2 degrees using an inverse tangent. And so we've got now the theta games would give us 2 theta p plus the pink theta would be equal to 180. That would be a strike in the counterclockwise direction. Go ahead and plug in the pink theta. We find that theta p is equal to 47.4 degrees counterclockwise, or if we went the other way, we would end up with 42.6 degrees. And so just for completeness, right, if we used positive 11.49, right, we're talking about positive as drawn on the cube, and it was drawn in that orientation. So not to go too crazy on it, but these would be the answers for positive 11.49. The answers would be just slightly flipped if it were negative. You see the same numbers, just opposite directions. And although we've basically done it, right, sigma 1 would equal the center plus r. So there's the center value, there's the r value, giving us a principal stress of 23.06, and a maximum shear stress would just be equal to r, 11.53.